grade 12 learners. Welcome to today's physical sciences lesson. The lesson is brought to you by the Northern Cape Department of Education in collaboration with Parliament Research and Development. My name is Davezinhle Dliwayo. In our lesson today, we're doing a revision on the momentum and impulse. Momentum and impulse. So we're going to be attempting typical examination questions on our momentum and impulse. It is important that you remember that this actually is question 4 in our physics, that is our paper 1 examination. So at the end of the lesson, you should be able to attempt typical examination questions in the paper 1 question 4. So take note that we are going to be attempting different examination questions so that you're able to see how these questions are actually set up or designed so that you are able to tackle any kind of question pertaining to momentum and impulse. And I encourage you to work on the questions with me. I'm going to be giving you time to work on the questions. You can discuss with somebody next to you, do the calculations together so that you learn something at the end of the day. And I should say all the best as we do these calculations. So ensure that you have your calculator with you. Right, for our pre-knowledge covers the whole section on momentum and impulse. Remember, our section can be divided into 4 parts. The first part being a momentum. You do well to remember that our momentum, our P, momentum, which is a vector quantity, is equal to mass times the velocity of an object. Okay, mass measured in kilograms, velocity measured in meters per second. Hence, our units of momentum are kg meters per second. And also remember that momentum is a vector. Therefore, it means in your solutions, you need to take into account the aspect of direction. The second part is this Newton's second law in terms of momentum. Remember Newton's second law, F is equal to ma. But in terms of momentum, we know that our net force is going to be equal to the rate of change of momentum. That is delta P divided by delta T. Okay, remember that that relationship. And then the third part is the law of conservation of linear momentum and elastic and inelastic collisions. We are saying the sum of your initial momenta before collision is equal to the sum of your final momenta after collisions. Right? That is the conservation of our linear momentum. And when it comes to elastic and inelastic collisions, you also do well to remember that during an elastic collision, we are saying the sum of the initial kinetic energy is equal to the sum of the final kinetic energy. Our kinetic energy, in other words, is conserved. On the other hand, for an inelastic collision, we are saying your kinetic energy is not conserved. And last but not least, we talk of impulse, and the formula for you to recall, F net delta T is equal to delta P. And you can see this is actually derived from there. Okay, so F net delta T, that is our impulse. So generally, this is an overview of our section. And as I said, let us work on the examination questions, the kind of examination questions. We're going to start with a small question, an easy kind of question, so that you just get warmed up. Right, for our question 1, I'm going to give you 5 minutes, grade 12s, okay? So 5 minutes starting from now. Right, welcome back. Now let us look at the question together. So ensure that you take down the necessary points. Wherever you might have gone wrong, ensure that you do your corrections. Right. A bullet of mass 20 grams is fired from a rifle. Then we're saying the bullet passes through a plank of wood while traveling east. Its speed decreases from 300 meters per second before it hit the plank to 180 meters per second as it emerges out of the other side of the plank. Calculate, number one, the initial momentum of the bullet. Okay, so these are the steps that we're going to take. We're saying our east is positive, and therefore it makes our velocity there positive. It's 300 meters per second east. That one will also be positive because it is still in the same direction, that is east. Right, let's list our data there. What are we given? We're given the mass of our bullet. Our mass is given in grams. And remember, we say when we're dealing with momentum, our mass has to be in kilograms. So we change our 20 grams. I hope we didn't forget to convert our mass to grams. And I can see someone going, ish. Yes, don't make that mistake. Ensure that you change your mass to kilograms. So 20 grams is actually 0.02 kilograms. Our velocity, we're looking at the initial momentum. So we need the initial velocity, that is 300 meters per second, and therefore we can generate our pi, that is our initial momentum. So our formula, momentum is equal to mass times your initial velocity. We substitute the values there, okay, and then we get our mass. And we're saying this is our final solution. Take note, we have the unit as well as the direction. I hope you got that correct. And then the second part, the final momentum of our bullet, right? And we're saying our east is positive, and therefore our mass is still the same, 0.02 kilograms. Our final velocity is 180 meters per second. It's positive because it is still in the same direction, that is east. And therefore our PF, that is our final momentum, mass times final velocity, which gives us that, and we are getting 3.6 kilograms east, and this is positive. All right, that's how we get our final momentum. And then the change in momentum of our bullet, we remember well that change in momentum is equal to the final momentum minus the initial momentum. Already in our first part, in our part one, we calculated the initial momentum to be a positive 6 kilogram meters per second, and our final momentum was a positive 3.6 kilogram meters per second. Therefore, what is our delta P? Our change in momentum. Our change in momentum is final momentum minus initial momentum. Take note, grade 12s, it is important that you put your formula first. You see how we're laying out our calculations. All right, so the formula first, substitution, and then your solution with the appropriate unit and direction. Right, so our final is 3.6. Our initial is negative, is actually a positive 6, and then we get a negative 2 kilogram meters per second. And we're saying, what does the negative tell us? Our negative is showing us it is in the opposite direction to our reference positive direction. Our reference positive direction in this case, grade 12, is the east. So if we're getting a negative value there, it shows us that our momentum is actually west. Our change in momentum is west. Okay, definitely that was a refreshing question. Right, let's go on. Let's go further now, grade 12. Let's go to the next question, our question 2, taken from a past examination question. Right, we are going to go over this question together, but you are going to do the work first. All right, as I said, feel free to discuss with the person next to you. Okay, do the calculations together, answer the questions, All right, and then we'll discuss together. Right, so for this part, I'm going to give you 5 minutes. Right, welcome back. Welcome back. Now let us work on the question together. Now we have a trolley X of mass 1.2 kilograms, which is traveling. So these are the important details that we should take from our question. The mass, okay, travels 8 meters per second east. We have the graph there. You should be able to interpret the graph. And you can see your 8 meters per second there, which is the initial velocity of your trolley X. I hope you are seeing that. And it is positive. So it means our east is our reference positive direction. Are we following? And collides with trolley Y of mass 0.5 kilograms initially at rest. And that is telling us something about the velocity, the initial velocity of Y. What is it telling us? Grade 12. What is the velocity of Y? It is at rest. Therefore, its velocity is 0 meters per second. Take note, that is the initial velocity of our Y. And then ignore all frictional effects. The velocity time graph below shows the velocity of trolley X. I'm sure we can see that from the title then. Before and during and after the collision with trolley Y. Before attempting the questions, let's analyze this graph. Okay, from the graph we can see that the initial velocity of trolley Y, that one, that is the initial velocity of trolley X VI. Okay, and then this section, you see this section where the velocity is decreasing. This is the section of our collision. Okay, this is the section of our collision. And already, what are you noting? This time, which I'll call delta t, this is the time of our collision. This is the time of our collision, which is very important when we're now dealing with the question on impulse. All right? And then there, 4, that is the final velocity of x after collision. That is the information we are getting from our graph. I hope you were able to pick it up. Right, the first part, state the principle of conservation of linear momentum. Such sections you are guided by your examination guideline. That should be your best friend, grade 12. Someone is looking across the class saying, my best friend is sitting over there. Say, no, your best friend is the examination guideline. Are you listening to me, grade 12? Yes. So the principles, the definitions, all of them that you need to know, you find them in your examination guideline. And you can see there are 2 free marks. So you should be singing these definitions and principles. Our principle of conservation of linear momentum, it states that in an isolated, take note, these are keywords, in an isolated or closed system, the total, these are keywords, okay? The total linear momentum of an object is conserved or remains constant. You see, the terms I'm underlining, they are very important. They should appear. And remember, when you're stating principles or stating definitions, you should state them the way they appear as per examination guideline. That is why the exam guideline should be your best friend. Let's go to the second part. Calculate the magnitude of the velocity of trolley Y immediately after the collision. Right. So how do we go about that? Okay, we need to list our data that we need. In this case, we know that we are now dealing with the law of conservation of our linear momentum. So let's list the data that we have from our question so that we can be able to calculate the final velocity of our trolley Y, that is after the collision. Let's start with trolley X. What is the mass of trolley X? Mass of trolley X, yes, grade 12, is 1.2 kilograms. What is the initial velocity, or call it Vxi? The initial velocity of your trolley X, we're getting it from the graph there. Okay, it's a positive 8 meters per second. Okay, what is the final velocity of trolley X? I'll call it VXF. There we say it is what? It's a positive 4 meters per second. All right, let's look at trolley Y. Our trolley Y, what is the mass of Y? Our mass of Y, we're given there, is 0.5 kilograms. And what is the initial velocity, VYI, the initial velocity of trolley Y? Remember, we're told initially at rest. That is communicating something to you. That is 0 meters per second. What is the final velocity of trolley Y? This is what we want to calculate. This is all the data that we need to calculate the velocity of trolley Y immediately after the collision. So we're using our law of conservation of linear momentum, which states that the sum of momentum, that is the initial momentum before collision, is equal to the sum of your final momentum after collision. Right? And what does this translate to? What is our initial momentum? Okay, we're taking the mass of X multiplied by the initial velocity of X, that is Vxi, plus the mass of Y multiplied by the initial velocity of Y. Okay, so this is the sum of our initial momentum before collision. It's going to be the mass of our X multiplied by the final velocity of our X, that is after collision, plus the mass of Y multiplied by the final velocity of Y after collision. Okay, so now you see that we listed our data here. So now what are we doing? We're just picking our data, plugging into the formula. And already these two parts, they all constitute just a single mark. This is one and the same thing. For listing that formula, you're getting your single mark. Then we go to the next part, substitution. Mx is 1,2. Okay. Vxi, it's a 8. Right. Plus My, it's a 0,5. I hope you're also writing grade 12s. And then VIY, it's a 0. We're substituting. You cannot fail to substitute from the data there. Mx, we said it is 1,2 kilograms. Vxf, it's a 4. All right. Plus My, 0,5. Then our VYF, the one that you want to calculate. And for this part, again, you're going to get a single mark for this side, for the initial momentum calculation, and another mark. At this stage, you can see now you're already at 3 marks, grade 12. And then what was I saying now? The rest is mathematics, your calculator, solving the equation, solve for VYF. Can you do that? What value are you getting? Let's do the calculation. Finish it up. Grade 12, we're getting what? VYF. That is the final velocity of our trolley Y after the collision. We are getting a positive 9,6 meters per second. So if it is a positive 9,6 meters per second, what is it telling us? Remember, our reference positive direction is the east, right? So it means this is actually going to the east. But remember, the question said the magnitude. So we don't care about the direction at this point because we just need the magnitude. That is the size of our velocity. But we know that it is going east. And I hope you got it correct. Okay. Let's go to the next part. Calculate the magnitude of the average net force. The moment you see average net force now, you're already thinking, oh, impulse, something to do with impulse. And we know the formula that you need to apply, something to do with the time. That trolley X exerts on trolley Y during the collision. Remember we said this section, this is the time. This is the section of our collision, grade 12s, when the velocity is actually decreasing at a uniform rate. Okay, so what is important is for you to get that time, delta, or delta t. So what is our delta T? Our delta T is going to be 20,02 minus 20,1. Oh, it's 20,2 minus 20,1. Definitely this gives us 0,1 seconds. That is the time of our collision, 0,1 seconds. Right, so we need our formula, and we're saying F net delta T is equal to what? Is equal to delta P. We're dealing with trolley X. Don't forget the average net force that trolley X exerts on trolley Y. So whatever we're doing there in our calculation, we should be using details of what our trolley X. Okay. So let's go ahead with our calculation there, grade 12. F net, this is the force that we need to calculate. What is our delta T? Our delta T is 0,1 seconds, right? And then what is our delta P? Our change in momentum. I said, remember, we need to use the details of trolley X. Remember, change in momentum, your delta T, your delta P is the mass multiplied by the final velocity minus the initial velocity. You realize now what we've all been doing now is formulas and substitution. So it is important that you master your formulas. If you have a question, you should be able to identify, okay, in this case, I'm supposed to use this particular formula, and you won't go wrong. So what is the mass in that case? We're saying is 1,2, right? The mass. Remember, we're dealing with x. Okay. And then final velocity of x, we say that is the VF for x. Final velocity is 4, right? Initial velocity, there is our initial velocity. It's 8. Oh, definitely we're going to get a negative. Let's do the calculation there. What are we getting? Grade 12. F net. Our F net is going to be what? What value are you getting? Can you punch in the calculators there? We're getting an F net of 48 newtons. Okay, so again, we're interested in the magnitude and not the direction, isn't it? It's a negative. Okay, it's a negative, definitely. 4 minus 8 gives us a negative. So it's a negative 48. Already, this is telling us something. Our reference positive direction is east. So if we're getting a negative, therefore, our net force has to be in the opposite direction, which is west. So a mark there, and a mark there, you get your 3 marks. Okay, let us proceed. Is the collision elastic or inelastic? Explain the answer by means of a suitable calculations. 5 marks. These are nice marks. 5 marks. Right. The first thing in dealing with such a question is for you to reflect on your understanding of elastic and inelastic collisions. And you do well to remember that for elastic collisions, we're saying your kinetic energy is conserved. And that means your final kinetic energy is equal to the initial kinetic energy. And therefore, this actually guides us. Okay, this actually guides us now as to the direction we should take. We should do calculations to do with kinetic energy. And we remember, when we're talking of kinetic energy, we need this formula. Kinetic energy is equal to what? Half mv squared. Okay. This is the formula that guides us, and it gives you a mark. And then we're saying now, we need the sum of the initial kinetic energy. Let me write it here. The sum of our initial kinetic energy, which I'll call EKI, isn't it? It should be equal to the sum of what? Of the final kinetic energies, grade 12. If this is satisfied, then we know that the collision is elastic. If they are not equal, then the collision is inelastic. Are you getting the direction? So let's start by calculating our what? let's start by calculating our initial, the sum of our initial kinetic energies, grade 12. So we need the kinetic energy of trolley X. We need the kinetic energy of trolley Y. Their initial kinetic energies. We get the sum. That will give us the initial kinetic energy. Are you following? So we're saying mx, the mass of x, multiplied by the initial velocity of x squared plus half my multiplied by y, multiplied by the initial velocity of y squared. You see, everything lies with the formulas, grade 12. Then let us substitute then. Have mass of our trolley X, we say that is what? 1,2 kilograms. And the initial velocity, we have it there, it's 8. Everything is there for you, grade 12s there. Half mass of trolley Y. Remember, we say the mass of our trolley Y is what? 0,5. Okay, and what is the initial velocity of trolley Y? We say trolley Y is at rest. Initial velocity, it's 0. Okay, so can you do the calculation there? Let's just do the math. What value are we getting? We are getting a value of 38, should be 38,4 joules. Remember, energy is not is in joules. So this is our initial kinetic energy. Okay, sum of our initial kinetic energy in the collisions. And then let's go and calculate the final kinetic energy, right? The sum of the final kinetic energy is half mx. We're looking at the final velocity now of x squared plus half my, the final velocity of y squared. You see that? Okay, and then we substitute now. Let's substitute half. What is the mass of x? 1,2. What is the final velocity of our x? It is 4 plus half mass of y 0,5, and the final velocity of y. Remember, we calculated it in our previous section. And you see now the importance of doing the calculations correctly, because if you got the question wrong, if you got the velocity wrong on the other part, it means your solution in this part is going to be wrong. So we got a value of 9,6. Okay, and we're saying that also squared. Okay, so we can calculate now, and we are getting a value of 32,64 joules. Right, this is the final, okay, the sum of the final kinetic energies. And you agree with me? Let me take you back. Initial kinetic energy, check, 38,4. Do we note that? Okay, and then what is our final? 32,64. So what can we conclude? We can conclude that the sum of our final kinetic energy is not equal to the sum of our initial kinetic energies. Therefore, the collision is what? The collision is inelastic. So that is the calculation that we needed to prove that. As long as the sum of the initial kinetic energy is not equal to the sum of the final kinetic energies, then we're saying our collision is inelastic. I hope you see what we did there, grade 12. Right, let us proceed to question 3 and be taking note of how these questions are structured. So in our question 2, we actually noted that our question on momentum and impulse can be approached in a graphical sense. So you should be able now to interpret the velocity time graphs for your collisions. Okay, so in the velocity time graph, you are expected to be able to take note of the initial velocity, the final velocity, the time taken for the collision. Is it making sense, grade 12? So as long as you're able to interpret the graph, you're able to pick the data from your graph, and then the rest is application of the law of conservation of our linear momentum. Right, let's look at this question. It looks also interesting. Question 3. Right, for this part, I'm going to give you another 5 minutes. 5 minutes. Talk to your partner there. Let's do the calculations. Let's work. 5 minutes. Right, welcome back. Welcome back. Right, we have trolleys there. A of mass 1 kilogram. This is our A, so we know that our MA is equal to 1 kilogram, right? And then B of mass 2 kilograms. So we know our MP is equal to 2 kilograms. Are held stationary. Okay, if they are held stationary, what does that tell us? Be picking up your data from the question. It tells us what is the velocity. We call it MBVI. The initial velocity of B is 0. What is the initial velocity? Okay, it's not MBV. The velocity of B, initial velocity of B is a 0, right? And then also the initial velocity of A is also a 0 because they are stationary. So already this is the information we are picking from the question. Before we even start answering the questions, right, on a smooth horizontal surface with a compressed spring between them, as shown in the diagram below. So this is typically a setup that is an explosion. Remember momentum, we have collisions and explosions, right? Now the spring is released and falls to the ground. Trolley A moves to the right at constant velocity of 5 meters per second. Okay, so we know now VA final is 5. We can call it a positive 5 if we take the direction to the right as positive and collides with the wall. Oh, quite an interesting question. Now assume this is an isolated system. Remember, in the law of our conservation of momentum, we use the term isolated. So define an isolated system. As a reminder again, these terms, you find them in your examination guideline. There is no definition, there is no principle that you may be asked to define or state in an examination. That does not exist in your examination guideline. So when the examination comes, it will not be a surprise to you, grade 12s, and start saying, I never came across this definition in my preparation. All the terms you need to define are there in the examination guideline. And the definitions that are required of you are also there in the examination guideline. And I will repeat, make it your best friend. And these 2 marks are for free for you. So an isolated system is a system on which the net external force is equal to 0. As simple as that. F net is equal to 0. Right, now calculate the velocity of trolley B immediately after the spring is released. Conservation of linear momentum. All right, let's list our data here so that we remember what we need. What are the values? Okay, we know our MA, the mass of A, we're told is 1 kilogram. Okay, and what else do we know? Our MB, we're told, is 2 kilograms. This is the data that you need. Right, and for both A, VAI, and VBI, their initial velocities, remember we said these are at rest. So both of them, they've got initial velocities of 0 meters per second, right? What else do we need? We have the final velocity, I'll call it VAF. We say it is a positive 5 meters per second. And now you need to calculate the velocity of what? Of trolley B after. So we need VBF, the final velocity of, of what? Of B after the spring is released. Okay, so this is our data. Now that we have our data, we now apply the law of conservation of linear momentum. So we know the sum of the initial momentum is equal to the sum of the final momentum after the collision. Right. So stating this, it constitutes a single map. Remember that the sum of your initial momentum is equal to the sum of the final momentum. MA, we know it is 1 kilogram. VI, we know it is a 0. Right. So both A and B are stationary initially. So we know that their sum is going to be equivalent to a what? To a 0. And then you're using the final then. Okay, substitute. The mass of A is 1. The final velocity of A is 5 meters per second, right? And then the mass of B, we know that is 2. The final velocity is the one that we want to calculate then. Right. So now we can substitute there into the formula. And what are we saying? What value are we getting there? What value are we getting? We're getting a negative 2.5 meters per second. Remember, we are calculating the velocity in this case, not the magnitude. So it means the direction is needed. And remember, we said to the right is positive. Why? Because we're saying the value of final velocity of our A is positive as it goes towards the wall. It's positive. So it means now, if our final velocity is a negative, what does it tell us about the direction of B? It means B is actually moving at 2.5 meters per second to the what? To the left. So B goes that way while A goes that way. And makes sense, really, isn't it? Okay, right. I hope you were able to get that one correct, grade 12s, right? Let us clap hands for those of us who got it correct. Let's clap hands. Okay, thank you so much. Right, let us proceed to the next part. Okay, we're saying the average force exerted by the wall. Well, we're looking at the wall, isn't it? On trolley A is 80 newtons. Now we're thinking of Newton's third law, action reaction. If a force A exerts a force, if an object A exerts a force on object B will exert an equal but opposite force on object A. So already this is telling you something. Trolley A is exerting a force of 80 newtons. So what is the force that will be exerted by the wall on trolley A? It will be equal but opposite. So it means the wall is going to exert a force of negative 80 newtons on trolley A. Are you following? Right. And the collision of the trolley with the wall lasts 0.5 seconds, delta T. This is now collision. Already the formula that is coming into mind, F naught delta T is equal to delta P. That is the formula that is coming into mind. Now calculate the velocity with which our trolley A moves away from the wall. So now, how are we going to go about it? The first thing is our formula. Okay, F net delta T is equal to delta P. Remember, what is our delta P? Our delta P is mass multiplied by the final velocity minus the initial velocity. We're saying change in momentum. It starts from here as a reminder. Change in momentum is final momentum mvf minus mvi. And remember, we're just using our mathematics there to factorize to lead us to that simplified version of our formula, right? So we're looking at the wall, the force that the wall actually is exerting on A. So F net delta T is equal to M delta V, isn't it? M delta V, and this is our delta V. Okay, and we're saying MVF minus MVI. We're still expanding the same formula so that you may understand where this is actually coming from. Right, so what is our F net? Remember, we said our F net is a negative what? It's a negative 80. That is the force from the wall. Okay? And then our delta T is 0.5 seconds given by the question there. And then what is the mass? Our mass is 1 kilogram. The mass of A is 1 kilogram. Right? And what is the final velocity there? It is what we want to calculate. Okay? And then mass is 1. The initial velocity, we know that it is 5 meters. After the spring drops, trolley A approaches with a positive velocity of 5. You have your formula now, you have your equation, you have substituted. Let's solve for our VF. We're getting a positive 1 meter per second. So this is the velocity with which it is going to leave the wall. It will leave the wall with a velocity of 1 meter per second. Right, I hope you were able to get that grade 12. Right, a learner comments that the collision of trolley A with the wall is inelastic. Okay, the collision of A with the wall is inelastic. Briefly explain what is meant by an inelastic collision. Remember, in an inelastic collision, kinetic energy is not conserved. We have a change in kinetic energy. And you do well to remember that your kinetic energy, EK, is half mv squared. And when you're dealing with an object, a particular object, you know that the mass will never change, right? So what is going to determine that the kinetic energy is going to change or not in a collision is what? The velocity. The moment the velocity of an object changes, then you know that the kinetic energy of your object has changed. Let's look at trolley A. When trolley A moved towards the wall, its initial velocity, we said it was a positive 5 meters per second, right? And when trolley A bummed on the wall and came back, which is the last part that we did on our calculation, what was VA final? Going back, we got 1 meter per second. So already you can see there is a change actually there in the velocity of A before and after the collision with the wall. V has changed. It means our EK has changed. Therefore, there is no conservation of our kinetic energy, and that renders our collision inelastic. Are you following grade 12? So we're saying an inelastic collision is a collision where our kinetic energy is not conserved. Are we following? Right. So the total kinetic energy before the collision is different from the total kinetic energy after the collision. Is it making sense? Right. I hope you were able to get that, and then you get your two marks there. Right. Now we've come to the end of our lesson for today. But as usual, I'm not going to leave you empty-handed there. I have some questions for you for your homework, for you to actually practice, right? And see whether you understood. This is also a typical examination question, grade 12s. You can copy it, all right? And then you discuss with your friends, you work out the question. And again, I'll urge you to look for more typical examination questions on your momentum and impulse, right? That being said, we have come to the end of our lesson for today. I hope you found the lesson quite informative. Till we meet again, may God bless you.